Beneath your feet, if you could somehow stand on Mercury's surface, protected from the extremes, the ground would feel unlike any terrain on Earth. The surface is covered in a layer of loose material called regolith, broken rock fragments and dust accumulated over billions of years of meteorite impacts. This powdery layer resembles very fine sand mixed with gravel, each grain sitting loose against its neighbors, without any moisture or atmosphere to bind them together. Your footprints would press into this ancient dust and remain there indefinitely, preserved for millions of years with no wind or weather to erase them. The color stretching in all directions is a dark gray, similar to charcoal or weathered concrete, covering the landscape in muted tones. Mercury's surface is actually darker than our moon's surface, reflecting only about 12% of the sunlight that strikes it. This low reflectivity comes partly from the presence of carbon-rich minerals mixed into the regolith, and partly from tiny particles of metallic iron scattered throughout. The darkness gives the landscape a somber, ancient quality, like standing on ground that has absorbed eons of cosmic history. You are listening to the Drowsy Astronaut, and tonight we step onto the surface of Mercury, the closest planet to the Sun. There is no rush in this exploration, no timeline to follow, no information you need to remember by morning. We will simply spend time on this alien surface, exploring what the ground looks like, what it is made of, and what 4.5 billion years of exposure to space has created here. If you enjoy this journey, feel free to leave a comment about where you are listening from tonight, and perhaps a like or subscribe if the channel helps you rest. Looking down at the material directly beneath you, the texture would remind you of talcum powder in some places and coarse sand in others. The regolith particles range from dust grains too small to see individually to pebbles and rocks the size of your fist or larger. This mixture formed not through the familiar erosion processes of Earth, wind and water breaking down rock, but through something called impact gardening. Every meteorite that strikes Mercury, from microscopic dust to boulder-sized rocks, pulverizes a small amount of surface material and throws it into the air. Over billions of years, countless impacts have ground down the bedrock beneath, creating a layer of broken fragments several meters deep. The depth varies from place to place, typically ranging from about 2 meters to 10 meters or more, depending on local history. In some areas where large impacts occurred relatively recently, the regolith might be thinner, exposing fresher bedrock beneath. In other regions that have remained undisturbed for billions of years, the layer of fragmented material has grown thicker and finer. The regolith is not uniform in composition across Mercury's surface, though the differences are subtle to the eye. Some regions contain slightly more iron, others show higher concentrations of sulfur compounds, and certain areas display unusual amounts of volatile elements, like sodium and potassium. These compositional variations reflect differences in the bedrock below, and also record the arrival of different types of meteorites over geological time. Each impact that contributed material to the regolith brought with it the chemistry of whatever object struck the surface. Scattered across this grey powder, rocks protrude here and there, their surfaces rounded and pitted by micrometeorite impacts accumulated over eons. These rocks are not separate from the landscape, but rather larger fragments of the same material. Pieces that have not yet been ground down to dust. Some show angular faces where they have been fractured by impacts, while others appear more rounded, their edges softened by billions of years of bombardment. The surfaces of these rocks are darker than fresh breaks would be, space weathering having altered their outer layers. The space weathering process happens slowly but relentlessly as the solar wind, a stream of charged particles from the sun, strikes exposed surfaces. This bombardment changes the chemistry of the topmost layers, darkens the material, and creates tiny glass droplets where micrometeorites vaporize small amounts of rock. The glass beads, microscopic spheres formed in the violence of high-speed impacts, are scattered throughout the regolith. If you could examine the dust under magnification, you would find these tiny, perfect spheres mixed among the angular rock fragments. Beneath the regolith layer lies bedrock, the solid foundation that has been ground down over the ages to create the loose surface material. This bedrock consists primarily of basalt, a type of volcanic rock that formed from cooling lava billions of years ago. Mercury experienced widespread volcanic activity in its early history, with lava flows resurfacing large portions of the planet and filling impact basins. The basaltic bedrock tells this story of ancient volcanism, though the volcanoes themselves have long since gone cold and quiet. The basalt on Mercury differs slightly from Earth's basalt in its composition, containing less iron and more sulfur than typical terrestrial volcanic rocks. This difference reflects the conditions under which Mercury formed, closer to the Sun where the solar nebula was depleted in volatile elements. The volcanic rocks crystallized from magmas that rose through Mercury's interior during the first billion years or so of the planet's existence. After this early active period, volcanic activity gradually ceased as the interior cooled and the planet's outer shell thickened. Walking across this surface, you would notice that the regolith provides relatively firm footing despite its powdery nature. The grains pack together under pressure, supporting weight reasonably well, though you would certainly sink in a few centimeters with each step. The material has no cohesion, no water to create surface tension, no organic matter to bind grains together. So footprints compress the material, but do not create the kind of firm impressions you might make in damp sand. Instead, the compressed regolith holds its shape purely through the mechanical interlocking of angular particles. The temperature of the ground beneath your feet would depend entirely on whether you stand in sunlight or shadow, a stark division we will explore more thoroughly as our journey continues. For now, we can observe that the regolith serves as an insulator, its loose structure trapping tiny pockets of vacuum between grains. Heat does not conduct well through this material, meaning that just a meter below the surface, temperatures remain relatively stable compared to the extreme swings experienced at the surface itself. The insulating properties of regolith are why NASA missions to airless bodies must sometimes drill or dig to reach material whose temperature reflects deeper conditions. Certain regions of Mercury's surface show features called hollows, bright, irregular depressions scattered across crater floors and walls. These hollows appear to form where material has somehow been removed from the surface, though the exact process remains somewhat uncertain. One possibility is that volatile compounds buried in the regolith sublimate, change directly from solid to gas when exposed to sunlight, leaving behind the brighter, slightly depressed areas. The hollows are relatively small, typically tens to hundreds of meters across, but they stand out visually against the darker surrounding terrain. The presence of volatiles, like sulfur in Mercury's crust, might seem surprising given the planet's proximity to the Sun and the intense solar radiation. However, the materials in question have high enough boiling points to remain stable under most surface conditions, only sublimating under particular circumstances. The hollows may mark places where these compounds were concentrated in subsurface layers and then exposed by impacts or other processes. Their brightness compared to the surrounding terrain suggests they expose relatively fresh material not yet darkened by space weathering. Looking across the landscape from any vantage point, the surface extends to a horizon that appears closer than Earth's horizon would from the same height above ground. Mercury is a smaller world than Earth, with a radius of only about 2,440 kilometers compared to Earth's 6,370 kilometers. This smaller size means the horizon is only about 3 kilometers away if you stand at average height, compared to about 5 kilometers on Earth. The curvature of this smaller world makes itself apparent in the closeness of the horizon line. The ground shows subtle variations in elevation as you scan the distance, gentle slopes and rises that speak to the landscape's complex history. Some areas are relatively flat, filled with ancient lava, or smoothed by billions of years of meteorite bombardment. Other regions show more relief, with ridges, hills, and the rims of craters creating a rolling topography. The overall impression is of an ancient, stable surface that has not seen significant geological activity in billions of years, a frozen record of the planet's violent youth, now settled into quiet old age. What you cannot see, but what nonetheless affects everything around you, is the complete absence of any erosion in the familiar sense. There is no rust forming on iron-rich minerals, no dissolution of rock by acidic water, no expansion and contraction from freeze-thaw cycles involving ice. The only erosion mechanism is impact gardening, the slow grinding down of rock by meteorites of all sizes. This gives Mercury's surface a timeless quality, features persisting for billions of years in forms that would have long since eroded away on Earth. The regolith beneath your feet is not simply a curiosity, but a scientific archive, each layer recording different periods in Mercury's and the solar system's history. Impacts that occurred 4 billion years ago left their chemical signatures mixed into deeper layers, while more recent impacts contributed material to the upper layers. If you could dig down through the regolith and analyze each level, you would essentially be reading backward through time, sampling the flux of impactors across billions of years. Scientists who study samples of lunar regolith, which formed by similar processes, use this technique to understand the history of the inner solar system. The surface composition also reflects Mercury's unusual bulk composition, with a much higher proportion of metal to rock than any other terrestrial planet. This metal enrichment does not mean the surface is metallic. The iron is mostly locked into minerals rather than existing as pure metal, but it does contribute to the overall density and properties of the regolith. Understanding why Mercury has this composition requires looking at the planet's formation and early history, questions we will explore later in our journey across this remarkable world. Standing on this ancient surface, surrounded by grey regolith, that has been accumulating since the solar system was young. You would be standing on one of the most unchanged surfaces in the inner solar system. The ground beneath your feet connects directly to the planet's formation, modified only by impacts and not by the plate tectonics, volcanism, and erosion that continually renew Earth's surface. This is a landscape that remembers, preserving in its layers and fragments the record of billions of years. And across this preserved surface, craters of every size mark where the sky occasionally sent messengers in the form of high-speed rock and metal. The landscape, stretching in every direction from where you stand, is dominated by a single type of feature, repeated endlessly in sizes, from barely visible to encompassing the horizon. Impact craters cover Mercury's surface more densely than any other planet in the inner solar system, a testament to billions of years of bombardment. These circular depressions range from tiny pits a few meters across, barely distinguishing themselves from the surrounding terrain, to massive basins hundreds of kilometers wide. Each one marks a moment of violence when rock or metal from space struck the surface at tens of kilometers per second. The craters overlap one another in complex patterns, younger impacts cutting into older ones, smaller craters scattered across the floors of larger ones. This overlapping creates a palimpsest, a surface written and rewritten countless times, where earlier features remain partially visible beneath later modifications. The density of cratering tells scientists about surface age. Regions with many craters are older, their surfaces having been exposed to bombardment for longer periods. Areas with fewer craters are younger, having been resurfaced more recently by volcanic activity or other processes that erased the earlier impact record. Looking toward the nearest large crater, you would see a circular depression surrounded by a raised rim that casts deep shadows in the harsh sunlight. The rim formed when the impact explosion threw material outward from the point of collision, piling it in a ring around the newly formed crater. Material ejected from the impact landed across the surrounding area, creating a blanket of debris that thins with distance from the crater. This ejecta blanket covers and modifies the pre-existing terrain, burying older features and creating a slightly rougher texture than undisturbed regolith. The crater floor lies below the level of the surrounding terrain, excavated by the tremendous energy of the impact. For small craters, the floor is simply a bowl-shaped depression, the simplest geometry created by an explosion in solid ground. Larger craters show more complex features that formed during and after the impact event. When the crater exceeds about 15 kilometers in diameter, on Mercury, the floor often appears flat rather than bowl-shaped, filled with material that either melted during the impact or flowed in afterward. This flat floor creates a contrast with the surrounding elevated rim, a dark, smooth surface enclosed by the brighter, rougher rim materials. Many of the larger craters display a central peak, a mountain, or cluster of mountains rising from the crater floor. These peaks formed through a process called rebound, occurring seconds after the initial impact. When the impactor struck, it compressed the rock beneath the impact point tremendously, displacing material downward and outward. After the compressive forces from the impact passed, the compressed rock beneath the crater floor rebounded upward like a slow-motion splash. The center of the crater floor rose up, creating a peak or peak ring before the material lost momentum and solidified in its elevated position. The central peaks provide valuable scientific information because they excavate material from beneath the surface, bringing deeper rock up where it can be studied remotely. The composition of central peaks sometimes differs from the surrounding terrain, revealing what lies buried beneath. The peaks themselves can rise several kilometers above the crater floor, substantial mountains created in moments of violence. From the floor of a large crater, looking up at the central peak, you would see a mountain that exists only because of the rebound from an ancient impact. Walking toward the rim of a large crater, you would eventually encounter the terraced walls that characterize the largest impacts. These terraces form when the crater walls become unstable after the initial excavation and slump downward in massive landslides. The material slides in blocks, creating a stepped appearance like giant stairs leading down to the crater floor. Each terrace represents a place where a large section of the wall broke loose and moved downward, its motion stopped by friction and the geometry of the crater. The terracing makes the walls look less like smooth slopes and more like a stadium, with multiple levels stepping down toward the center. Some craters show bright rays extending outward from the rim for hundreds of kilometers, streaks of brighter material radiating across the darker terrain. These rays consist of material thrown out during the impact, fragments and dust that traveled great distances before falling back to the surface. The rays appear bright because the material is freshly exposed rock that has not yet been darkened by billions of years of space weathering. Over time, the solar wind and micrometeorite impacts will darken these rays until they fade into the background terrain. But for now, they mark the youngest and most recent large impacts. One crater on Mercury, named Hokusai, displays particularly prominent rays that extend over 1,000 kilometers from the crater rim. The rays cross older craters and other features, lying on top of them like paint splattered across a canvas. Hokusai itself is about 114 kilometers in diameter, a substantial crater, but far from the largest on Mercury. The prominence of its rays tells us it is geologically young, perhaps only formed within the last billion years or so. In the context of solar system history, this makes Hokusai almost a fresh wound on the ancient surface. The distribution of craters across Mercury's surface is not entirely uniform, though craters appear everywhere. Some regions show higher crater densities than others, indicating older surfaces that have accumulated impacts over longer periods. The oldest surfaces on Mercury are believed to be around 4 billion years old, dating back to the period of heavy bombardment when the inner solar system was still being cleared of debris left over from planet formation. These ancient surfaces are saturated with craters, meaning new impacts now mostly hit existing craters rather than pristine terrain. Other areas show lower crater densities because they were resurfaced by volcanic activity after the heavy bombardment period ended. Lava flows filled and covered older craters, creating smoother plains with fewer impact scars. These plains are called smooth plains by planetary scientists, a descriptive name that captures their appearance relative to the heavily cratered highlands. The smooth plains are not entirely smooth. They still have craters, but they have significantly fewer than the oldest regions. The difference is visible even in images from orbit, with the smooth plains appearing lighter and less textured than the densely cratered terrain. Crater chains appear in some locations, linear arrangements of craters stretching across the surface like beads on a string. These chains likely formed when a single object, already broken into fragments by a previous close encounter with Mercury or the Sun, struck the surface along a line. Each fragment created its own crater, and the fragments' shared trajectory meant they hit along a relatively straight path. Alternatively, some crater chains might be secondary craters formed by chunks of material ejected from a single large impact, falling back to the surface in a linear pattern determined by the ejection geometry. Secondary craters are common around large impact sites, smaller craters created not by independent impactors from space, but by debris thrown out from a primary impact. These secondary craters tend to cluster near the primary crater and often show distinctive features like elliptical rather than circular shapes, indicating they were formed by relatively low velocity, low angle impacts. Distinguishing between primary craters formed by objects from space and secondary craters formed by local ejecta is important for understanding the true impact rate Mercury has experienced. The walls and floors of many craters show additional small impacts that occurred after the initial crater formation, a record of continued bombardment over geological time. A crater that formed 3 billion years ago has had 3 billion years to accumulate smaller impacts within and around it, and the density of these later impacts provides information about the crater's age. Scientists use crater counting as a tool for determining surface ages throughout the solar system, a technique that works because impact rates decrease predictably over time. Some craters appear degraded, their rims worn down and their floors partially filled, indicating great age and subsequent modification. Others look fresh, with sharp rims and clean floors, suggesting relatively recent formation. The contrast between degraded and fresh craters creates visual texture across the landscape, different generations of impacts layered atop one another. Walking across Mercury's surface, you would constantly encounter these circular features, stepping over small crater rims, crossing ejecta blankets, and navigating the complex topography created by billions of years of impacts. The largest craters begin to merge into the category of impact basins, enormous features where the impactor was so large and the energy so great that the resulting structure extends across significant fractions of the planet. Mercury hosts several of these impact basins, each one representing a catastrophic event in the planet's early history. The basins are old, formed during the heavy bombardment period, when large objects still wandered through the inner solar system, occasionally striking planets with devastating force. One basin in particular dominates all others in size and significance, a structure so large that it affected the entire planet when it formed. The view from any point on Mercury's surface is likely to include multiple craters within sight, the landscape fundamentally shaped by impacts at every scale. This cratered terrain is what we recognize as the surface of an airless world, a planet without weather or erosion to erase the scars of impacts. Standing on Mercury, surrounded by craters near and far, you would be looking at a surface that has preserved its violent history with unusual clarity. And among all these craters, the blazing sun that makes all of this visible hangs in the black sky, enormous and brilliant beyond anything experienced on Earth. Looking upward from Mercury's surface, the feature that dominates everything is the sun, a disk of brilliance that appears roughly 3 times larger than it does from Earth. where the sun in Earth's sky spans about half a degree from edge to edge, approximately the same angular size as the full moon. From Mercury, it swells to about 1.5 degrees across. This larger apparent size results directly from Mercury's closeness to the Sun, orbiting at an average distance of only about 58 million kilometers, compared to Earth's 150 million kilometers from our star. The increased apparent size comes with a corresponding increase in brightness and intensity that makes the Sun an overwhelming presence. The amount of sunlight falling on Mercury's surface is roughly 7 times more intense than the sunlight reaching Earth, delivering about 9,000 watts per square meter at Mercury's closest approach, compared to Earth's 1,360 watts. This intensity creates conditions of heat and light unlike anywhere else on solid ground in the inner solar system. The Sun does not simply illuminate Mercury, it dominates the environment completely, determining temperature, surface chemistry, and the character of the landscape below. The Sun's disk appears sharp-edged against the black sky, its photosphere clearly defined without the softening effect of an atmosphere. On Earth, the Sun's light scatters in our atmosphere, giving it a slight blur around the edges and making direct observation impossible without eye damage. On Mercury, the vacuum allows you to see the Sun's edge with perfect clarity, though the brightness would still be far too intense for direct viewing without extreme protection. The surface of the Sun, visible from Mercury, shows the same features astronomers observe with specialized instruments: sunspots when they occur, faculae in active regions, the granulation pattern of convection cells covering the surface. The color of sunlight on Mercury is pure white, the full spectrum of the Sun's radiation reaching the surface without being filtered by an atmosphere. On Earth, our atmosphere scatters blue light more than other colors, making the Sun appear yellow or orange when we observe it through significant air mass. On Mercury, without any atmospheric scattering, the Sun's light maintains its full spectral balance, appearing as intensely white as it actually is. This white light creates stark illumination across the landscape, the contrast between light and shadow absolute in the absence of scattered light. Shadows on Mercury are completely black, regions of total darkness where sunlight does not reach, and no atmospheric scattering provides diffuse illumination. Standing in shadow, you would see nothing of the shadowed surface unless your eyes could detect the faint thermal radiation from the ground itself. The boundary between sunlight and shadow appears as a sharp line, no gradual transition or penumbra to soften the division. This stark contrast creates a landscape of extremes, where everything is either brilliantly lit or invisible in darkness, with no middle ground. The Sun's position in the sky determines local time on Mercury, just as it does on Earth. But the relationship between the Sun's position and the passage of time is far stranger here. The Sun moves across Mercury's black sky very slowly because Mercury rotates on its axis only once every 58.6 Earth days. This slow rotation means the Sun takes not hours, but Earth weeks to move from horizon to horizon. Watching the Sun in Mercury's sky, you would not see perceptible motion over minutes or even hours, but over days, you would notice it gradually shifting position. The motion becomes stranger still because of Mercury's elliptical orbit and the relationship between its rotation period and orbital period. Mercury orbits the Sun once every 88 Earth days, completing an orbit in exactly 1.5 Mercury rotations. This 3-to-2 resonance between orbit and rotation creates unusual effects in the apparent motion of the Sun across the sky. The relationship formed over billions of years through tidal interactions between Mercury and the Sun, with the Sun's gravity gradually slowing Mercury's rotation until it locked into this stable pattern. At certain points during Mercury's orbit, the Sun's motion across the sky appears to stop, reverse direction briefly, then resume its original course. This retrograde motion occurs because Mercury's orbital speed varies as it moves along its elliptical path. At perihelion, when Mercury passes closest to the Sun, the planet moves fastest in its orbit. At this point, the orbital motion temporarily overtakes the rotational motion from the perspective of someone standing on the surface. The Sun, which had been moving westward across the sky, slows, stops, moves backward toward the east, then stops again and resumes its westward journey. From certain longitudes on Mercury's surface, this retrograde motion of the Sun creates an even stranger effect, a double sunrise or double sunset. At these special locations, you could watch the Sun rise above the eastern horizon over the course of several Earth days, climbing slowly into the sky. Then, as Mercury reaches perihelion, the Sun would stop climbing, reverse direction, and set again in the east, where it had risen. After setting, it would rise again in the same place and resume its journey across the sky toward the western horizon. The entire process unfolds in slow motion, taking Earth weeks to complete. The longitudes where this double sunrise occurs are called the hot poles, though they are not at Mercury's geographic poles, but rather at specific points on the equator. These hot poles are the locations where the Sun is directly overhead when Mercury reaches perihelion, its closest point to the Sun. The combination of being closest to the Sun and having the Sun directly overhead creates the highest temperatures anywhere on Mercury's surface, with the ground reaching about 430 degrees Celsius. The Sun lingers at these hot pole locations, the retrograde motion causing it to spend extra time directly overhead, baking the surface longer than it illuminates other regions. Two hot poles exist on opposite sides of Mercury, separated by 180 degrees of longitude. The locations are defined by Mercury's orbital geometry, determined by the orientation of the planet's perihelion relative to its rotation. These points experience the most extreme heating in the entire inner solar system outside of the Sun itself. The ground temperature at the hot poles exceeds the melting point of lead, zinc, and many other metals that are solid at Earth's surface conditions. The Sun's heat radiates outward constantly, transferring energy to Mercury's surface through electromagnetic radiation across the spectrum from ultraviolet through visible light to infrared. Without an atmosphere to absorb or scatter this radiation, it strikes the ground directly with full intensity. The surface absorbs much of this energy, converting it to heat that raises the temperature of the regolith. The dark surface material absorbs more efficiently than it reflects, with the low albedo meaning that most incoming sunlight becomes heat rather than bouncing back to space. The energy from the Sun also drives chemical processes at Mercury's surface, breaking molecular bonds and ejecting atoms from the regolith. This process, called photon-stimulated desorption, contributes to Mercury's extremely thin exosphere the tenuous cloud of atoms surrounding the planet. Sodium and potassium atoms, knocked loose by solar radiation, form a faint glow detectable from Earth, though the density is far too low to constitute an atmosphere in any meaningful sense. The Sun continuously strips away surface material in this manner, atom by atom, while solar wind particles also sputter material from exposed surfaces. The Sun's radiation pressure and the solar wind it generates both affect Mercury strongly due to the planet's proximity and lack of protective atmosphere. The solar wind, a stream of charged particles flowing outward from the Sun, interacts with Mercury's weak magnetic field and also strikes the surface directly. These particles weather the surface materials, darkening them over geological time and modifying their chemical properties. The space weathering that gives Mercury its dark grey appearance results partly from this constant bombardment by solar wind. The apparent size and brightness of the Sun varies noticeably over the course of Mercury's 88-day orbit due to the elliptical path. At perihelion, when Mercury is 46 million kilometers from the Sun, the solar disk reaches its maximum apparent size and delivers maximum intensity. At aphelion, when Mercury recedes to 70 million kilometers distance, the Sun appears smaller and delivers less energy per square meter. The difference between perihelion and aphelion solar intensity is about a factor of 2.3, a variation far exceeding anything Earth experiences with its nearly circular orbit. This variation in solar intensity contributes to temperature variations on Mercury's surface beyond the day-night differences. The parts of Mercury experiencing daylight during perihelion receive much more energy than parts experiencing daylight during aphelion, even accounting for the Sun's position in the sky. The hot poles experience perihelion daylight, while points 90 degrees away in longitude experience aphelion daylight, creating a pattern of temperature variation locked to Mercury's orbital position. The Sun, in Mercury's sky, is not just a source of light and heat, but the dominant force shaping the environment, the primary factor determining surface conditions at any location and time. Its intensity creates the extreme temperatures. Its radiation weathers the surface. Its gravity shaped Mercury's rotation into the current resonance, and its wind of particles interacts with the planet constantly. Understanding Mercury requires understanding the Sun's overwhelming influence on this nearest planetary neighbor. And the Sun's light and heat play out against a sky that is always black, a darkness that makes the solar brilliance even more striking. The sky above Mercury remains black, even at noon, when the Sun blazes overhead with its full intensity, a darkness that seems contradictory but results directly from the complete absence of atmosphere. On Earth, the blue color of the daytime sky comes from our atmosphere scattering sunlight, with shorter blue wavelengths scattering more efficiently than longer red wavelengths. This scattering sends blue light in all directions, filling the sky with color and creating the familiar blue dome. Mercury has no atmosphere to scatter light, so photons from the Sun travel in straight lines from their source to the surface without deflection. The result is a sky as black as the depths of space, stars surrounding the Sun in a darkness that would seem more appropriate for night than for daytime. The contradiction between brilliant illumination at the surface and blackness overhead creates an environment unlike anywhere on Earth, where brightness and darkness coexist in ways our terrestrial experience does not prepare us to expect. The blackness is absolute, the same darkness visible from deep space or from the shadowed side of any airless world in the solar system. Stars would be visible during Mercury's day if you could shield your eyes from the sun's direct glare. Countless points of light surrounding the brilliant solar disk. The brightest planets would be visible as well. Venus, Earth, Mars, Jupiter, all appearing as bright stars in the black sky. Earth would appear as a blue-white point, its color not visible at this distance, but its brightness notable among the stellar background. From Mercury, Earth and the Moon would appear very close together, separated by only a small angular distance that would make them difficult to resolve as separate objects without magnification. The lack of atmospheric scattering means distant objects on Mercury's surface appear just as sharp and clear as nearby features, limited only by the curvature of the planet rather than by haze. On Earth, distant mountains appear bluer and hazier than nearby terrain due to light scattering in the intervening air. On Mercury, a crater rim hundreds of kilometers away appears just as crisp and detailed as one nearby, its clarity limited only by whether it is above or below the horizon. This exceptional clarity creates views that seem almost surreal in their sharpness, every detail preserved across vast distances. The horizon line itself is sharp and clean, the boundary where the surface curves away below your sightline, clearly defined, without atmospheric softening. On Earth, our horizon often blurs into the sky, the transition gradual through layers of hazy air. On Mercury's airless world, the horizon appears as a precise line, the last visible point of the surface, meeting the black sky with geometric clarity. The closeness of Mercury's horizon, due to the planet's smaller size, combines with this sharpness to create a landscape that feels more enclosed than Earth's open vistas. Without an atmosphere, sound cannot propagate from its source to your ears. No air molecules existing to carry the pressure waves we perceive as sound. Everything on Mercury happens in complete silence. Impacts of meteorites striking the surface produce no sound. Your own footsteps make no noise, and even the most catastrophic events occur without acoustic accompaniment. The silence is absolute and permanent, broken only by vibrations transmitted through solid material, like the ground beneath your feet. You might feel larger impacts through the surface, but you would never hear them through the vacuum above. The absence of atmosphere means no protection exists between the surface and the various forms of radiation arriving from the sun and from deep space. Ultraviolet light from the sun reaches the ground with full intensity, no ozone layer or other atmospheric component filtering it out. This UV radiation contributes to the surface chemistry, breaking chemical bonds and altering molecular structures in exposed materials. Over billions of years, this constant radiation has modified the surface composition, creating compounds that would not form or would not remain stable under Earth's atmosphere. Solar wind particles, primarily protons and electrons streaming outward from the sun, strike Mercury's surface directly in regions not protected by the planet's weak magnetic field. These charged particles impact individual atoms in the surface material, transferring energy and sometimes ejecting atoms into space through a process called sputtering. The continuous bombardment gradually erodes exposed surfaces at atomic scales, removing material so slowly that the effect is only significant over millions of years. Still, over geological time, Solar wind sputtering contributes to surface evolution and to the loss of volatile elements. Cosmic rays from beyond the solar system also reach Mercury's surface unimpeded. High-energy particles from supernovae and other violent events in the galaxy. These particles strike atoms in surface materials, occasionally creating new isotopes through nuclear reactions. The accumulation of these cosmogenic nuclides provides a way to date surface exposure ages, indicating how long particular materials have been exposed at the surface. On Earth, our atmosphere shields us from most cosmic rays, but airless worlds like Mercury preserve a record of cosmic ray exposure in their surface layers. Meteoroids of all sizes reach Mercury's surface without burning up. No atmospheric friction existing to heat and vaporize them before impact. On Earth, objects smaller than about a centimeter typically burn up completely in the atmosphere, never reaching the ground. On Mercury, even microscopic dust particles survive to impact the surface, contributing to the constant gardening of the regolith. The lack of atmospheric protection means Mercury's impact rate per unit area is higher than Earth's, though still far lower than during the heavy bombardment period early in solar system history. The vacuum above Mercury's surface is not absolutely perfect. Mercury does possess an extremely tenuous exosphere, a cloud of atoms that have been knocked off the surface but not yet escaped to space. This exosphere is so thin that it is effectively indistinguishable from vacuum for most practical purposes, with a density about 1 trillion times less than Earth's atmosphere at sea level. The atoms in the exosphere include sodium, potassium, calcium, magnesium, hydrogen, helium, and oxygen, each present in tiny quantities measured in atoms per cubic centimeter rather than molecules per cubic centimeter. These atoms reach the exosphere through several processes, including photon-stimulated desorption, where solar radiation ejects atoms, sputtering by solar wind particles, impacts of meteorites that vaporize small amounts of material, and diffusion from the interior. Once in the exosphere, atoms follow ballistic trajectories, arcing high above the surface before falling back down or escaping to space entirely. The exosphere is thickest near the surface and thins rapidly with altitude, extending hundreds to thousands of kilometers above the ground, depending on the species of atom and local conditions. Sodium and potassium in the exosphere glow faintly when excited by solar radiation, creating an extremely weak emission that can be detected by sensitive instruments on Earth. Astronomers studying this glow have mapped how Mercury's exosphere varies with location, time of day, and orbital position, finding that it responds dynamically to changing solar wind conditions and to the surface temperature variations. The exosphere represents the transitional zone between Mercury as a solid body and the surrounding space environment, a region where surface and space interact. The absence of a substantial atmosphere means no greenhouse effect warms Mercury's surface beyond the direct heating from absorbed sunlight. On Earth and Venus, atmospheric gases trap infrared radiation emitted by the surface, warming the planet beyond what solar radiation alone would achieve. Mercury's lack of atmosphere means its surface temperature responds directly to the balance between absorbed solar energy and radiated infrared energy, with no atmospheric layer to complicate the energy budget. This direct relationship creates the extreme temperature variations that characterize Mercury's environment. Weather as we understand it on Earth simply cannot exist on Mercury without an atmosphere to create winds, form clouds, or produce precipitation. Mercury experiences no storms, no winds, no clouds, and no seasonal changes driven by atmospheric circulation. The surface conditions change only through the very slow movement of the sun across the sky and through the occasional impact of a meteorite. The constancy of conditions in the absence of weather gives Mercury a static quality, the surface unchanging, except over geological timescales, measured in millions of years. The lack of twilight on Mercury creates abrupt transitions between day and night as the sun rises or sets. On Earth, twilight occurs because our atmosphere scatters sunlight even when the sun is below the horizon, providing diffuse illumination for some time before sunrise and after sunset. On Mercury, when the sun's disk drops below the horizon, darkness arrives immediately, the only light coming from stars and distant planets. Similarly, sunrise brings instant illumination as the sun's leading edge appears, no gradual brightening preceding the star's appearance. This airless environment creates an experience profoundly different from anywhere on Earth, a world where light and vacuum coexist, where the sky contradicts our expectations, and where silence reigns absolute. Standing on Mercury, under the black sky, surrounded by sharp shadows and illuminated by the brilliant sun, you would experience conditions unlike anywhere on Earth's surface. And across this airless, silent landscape, the largest impact scar on the entire planet stretches nearly 2,000 kilometers. A basin so vast that it affected Mercury's entire structure when it formed billions of years ago. Stretching across a significant portion of Mercury's surface lies the largest and most significant impact feature on the planet, a vast circular basin called Caloris. The basin measures approximately 1,550 kilometers across, a diameter roughly equal to the distance from New York City to Denver or from London to Moscow. Standing at the rim of Caloris, you could not see the opposite side. The far rim would lie well beyond the horizon, the curvature of Mercury's small globe hiding it from view. The scale of this feature exceeds anything you could fully appreciate from the ground, comprehensible only from orbital perspectives or through maps. Caloris formed roughly 3.9 billion years ago, when an object, probably exceeding 100 kilometers in diameter, struck Mercury at tens of kilometers per second. The impact energy released in this collision exceeded the combined explosive power of all nuclear weapons ever built by factors of millions or billions. The impactor vaporized on contact, its kinetic energy converting to heat and shock waves that propagated through Mercury's crust and deep into the interior. The surface at the impact point ceased to exist, as solid rock transforming instantly into plasma and vapor that expanded outward at tremendous velocity. The shock wave from the impact raced outward through Mercury's rocky crust faster than sound could travel, compressing and fracturing rock for hundreds of kilometers in all directions. The ground rippled like water struck by a stone, though at vastly larger scales, and moving at thousands of meters per second. Material excavated from the growing crater flew outward in all directions, some of it traveling fast enough to escape Mercury entirely and enter independent orbits around the Sun. Other ejecta fell back to Mercury's surface at distances ranging from tens to thousands of kilometers from the impact point, creating the secondary craters and debris fields visible around the basin today. The initial excavation created a bowl perhaps 10 kilometers deep and several hundred kilometers across, but this configuration proved unstable at such large scales. The crater walls collapsed inward almost immediately, slumping in massive landslides that created the terraced walls now visible around the basin's inner edge. The floor of the crater rebounded upward as compressed rock beneath the impact site bounced back, though at Caloris's scale this rebound created not a simple central peak, but rather a complex pattern of ridges and depressions. The final configuration stabilized within hours after the initial impact, leaving a multi-ring basin with concentric rings marking different stages of the shockwave and collapse. The basin floor today lies several kilometers below the surrounding terrain, a vast depression that has been partially filled by later geological processes. Smooth plains material covers much of Caloris's interior, believed to be volcanic lava that flowed into the basin some time after the impact occurred. The lava flooding may have happened shortly after the impact, taking advantage of fractures created by the collision, or it may have occurred hundreds of millions of years later during a separate phase of volcanic activity. The smooth plains appear light-colored in images due to their relatively young age and different composition compared to the surrounding ancient terrain. Wrinkle ridges cross the smooth plains floor in complex patterns. Low ridges formed when the cooling lava contracted and compressed. These ridges reveal that the lava cooled and solidified, then underwent further compression as Mercury's interior continued to cool, and the entire planet shrank. The ridges typically rise only a few hundred meters above the surrounding plains. Subtle features at the scale of the basin, but clearly visible in topographic data. The patterns they form reflect the stress patterns in the cooling and contracting lava and crust. The rim of Caloris is marked by mountains that rise up to 3 kilometers above the basin floor. Massive peaks formed by the uplift of material during the impact. These mountains are not volcanic in origin, but rather represent crust that was deformed and thrust upward by the energy of the collision. The rim mountains form a discontinuous ring around the basin, their exact heights and positions determined by the details of how the impact energy propagated through the heterogeneous crust. From the basin floor, these mountains would dominate the horizon in whichever direction you faced, their peaks catching sunlight while their lower slopes remained in shadow. Multiple concentric rings surround the central basin, visible as circular features in topographic maps and images. These rings mark the limits of different zones affected by the impact shock wave, each ring representing a place where the expanding wave created a particular type of deformation. The outermost ring reaches about 1,800 kilometers from the basin center, defining the Caloris impact structure as even larger than the visible basin itself. The rings give Caloris its classification as a multi-ring basin, a type of impact feature seen on other planets and moons when the impactor exceeds a certain size threshold. The impact that created Caloris affected the entire planet, not just the immediate impact area, through shock waves that propagated through Mercury's interior. Seismic energy from the collision traveled through the planet as pressure waves, compressing and expanding the rock as they passed. Some of these waves reached the opposite side of Mercury, the antipodal point exactly opposite Caloris, on the far side of the planet. There, the converging waves created unusual disruption of the surface, forming what is now called the chaotic terrain or weird terrain. This antipodal terrain consists of broken, jumbled blocks of ground extending across an area hundreds of kilometers wide, directly opposite Caloris. The blocks appear disrupted from their original positions, tilted and shifted in ways that suggest violent shaking from below. The correlation between this terrain and the Caloris antipode is too precise to be coincidental. The weird terrain formed when seismic waves from the Caloris impact converged on the far side, focusing their energy and literally shattering the surface. The formation of antipodal terrain from large impacts has been observed on other bodies and represents one of the most dramatic ways that major impacts affect entire planetary bodies. Caloris gets its name from the Latin word for heat, chosen because the basin sits near one of Mercury's hot poles, the longitudes where the sun is directly overhead during perihelion. This location means Caloris experiences some of the highest temperatures on Mercury, with the basin floor baking under the intense sun during the hottest part of Mercury's orbit. The naming is appropriate given the extreme thermal conditions, though the connection to heat is geographical rather than related to the impact that formed the basin. The age of Caloris, about 3.9 billion years, places its formation during the period of heavy bombardment when large objects still roamed the inner solar system in significant numbers. Caloris is one of the last major basins formed during this era, with most large impacts occurring earlier in solar system history. After Caloris formed, impact rates declined significantly as the solar system cleaned up its debris, and no comparable impacts have occurred on Mercury in the billions of years since. The basin represents the end of an era in Mercury's geological history, the last great restructuring of the surface. The volcanic plains filling Caloris tell us that Mercury's interior remained active for some time after the impact, able to produce magma that reached the surface and flowed across the basin floor. The composition of these plains differs slightly from older volcanic materials elsewhere on Mercury, suggesting that the planet's interior chemistry evolved over time as differentiation proceeded. Studying the Caloris plains provides information about Mercury's volcanic history and interior composition that cannot be obtained from more degraded older features. Future exploration of Mercury might include landers or rovers visiting Caloris, collecting samples from the basin floor and rim to better understand the impact event and the subsequent volcanic activity. The basin represents a natural laboratory for studying megascale impacts and their effects on planetary interiors. The samples would also provide precise ages for key events in Mercury's history, helping to calibrate the timeline of early solar system evolution. For now, Caloris remains a feature studied only from orbit, its full story still being deciphered from remote observations. The vast scale of Caloris means that if you stood anywhere within the basin, the feature would dominate your surroundings, though you might not immediately recognize that you were standing inside an impact structure. The horizon would look like a ring of distant mountains, the floor extending flat in all directions until it met those far peaks. The smooth plains would provide relatively easy walking compared to heavily cratered terrain, the surface interrupted only by wrinkle ridges and occasional later craters. Only from orbit does the circular nature of the basin become apparent, the grand design invisible to anyone standing within it. Caloris is not Mercury's only major impact basin. though it is the largest and best preserved. Other basins exist in various states of degradation, older features partially buried by later volcanic activity, or so heavily cratered that only traces of their original form remain. Mercury's heavily cratered surface testifies to the violence of the early solar system, when giant impacts were common rather than extraordinary events. But even in this context, Caloris stands out, the most recent and most visible of the mega impacts that shaped Mercury's current appearance. And across this impact-sculpted surface, other dramatic features mark where Mercury's interior evolution left visible scars in the form of vast cliffs that stretch for hundreds of kilometers. Crossing Mercury's surface in any direction, you would eventually encounter features unlike any impact crater or volcanic plain. Long, steep cliffs that cut across the landscape with no regard for the terrain they intersect. These features are called lobate scarps, and they represent thrust faults where one section of Mercury's crust has been pushed up and over another section in response to forces from deep within the planet. The scarps appear as winding cliffs that can stretch for hundreds of kilometers, rising anywhere from a few hundred meters to over 3,000 meters in height. They create barriers across the surface, steep slopes that would require significant effort to climb. The scarps formed as Mercury's interior cooled and contracted over billions of years, a process that continues even today, though at much slower rates than in the distant past. As the planet's large iron core solidified and shrank, the outer rocky layers had to accommodate the smaller interior volume. The crust responded to this compression by breaking along thrust faults, with some sections riding up over others to take up the slack created by the shrinking interior. The process is similar to how a grape becomes a raisin. As it dries, its skin wrinkling to fit the smaller volume inside, though the physics involved are obviously quite different. One of the most prominent scarps on Mercury carries the name Discovery Rupes, identified in images from the Mariner 10 spacecraft during its flybys in 1974 and 75. Discovery Rupes extends for approximately 650 kilometers across Mercury's surface, following a sinuous path that curves through multiple older features. The scarp rises over 3 kilometers in height at its tallest point, a cliff face that would tower over you if you stood at its base. The slope angle varies along the scarp's length, some sections rising at steep 45-degree angles, while others present more gradual but still substantial inclines. Another major scarp called Carnegie Rupes shows similar dimensions, stretching hundreds of kilometers and rising several kilometers above the surrounding terrain. Carnegie Rupes cuts through multiple craters, with the fault line crossing crater floors and slicing through walls without deviation. This cross-cutting relationship tells scientists that the scarp formed after the craters it intersects, providing relative age information. The scarp does not follow the path of least resistance, but rather cuts straight across whatever terrain exists, driven by the geometry of the underlying fault rather than by surface topography. The formation of these scarps required Mercury's radius to decrease by approximately 7 kilometers since the planet reached its current composition billions of years ago. A 7-kilometer decrease in radius translates to a 14-kilometer decrease in diameter and a reduction in surface area of roughly 100,000 square kilometers, an area comparable to the state of Kentucky or the country of South Korea. The entire crust had to compress by this amount, accommodating the smaller planetary volume through faulting and folding. The scarps we observe represent the visible expression of this global contraction, though not all of the contraction necessarily produced visible surface features. The compression affected the entire planet rather than being concentrated in one region, with scarps distributed across all latitudes and longitudes. This global distribution confirms that the cause was internal cooling and contraction rather than some external process. If the scarps were caused by impacts or other local processes, we would expect to see them clustered in particular regions. Instead, they appear everywhere, testifying to planet-wide compression from a shrinking interior. The pattern resembles Earth's tectonic features in some ways. But while Earth's plate tectonics arise from internal heat creating convection, Mercury's features arise from internal cooling creating contraction. Some scarps appear relatively fresh, with sharp edges and clear fault scarps, while others look more degraded, their profiles softened by billions of years of meteorite impacts and thermal cycling. The fresh-appearing scarps may have formed more recently, in geological terms, perhaps only a few 100 million years ago, rather than billions of years ago. This suggests that Mercury's contraction did not end in the distant past, but has continued throughout the planet's history. Recent analysis of high-resolution images from the Messenger spacecraft identified small scarps that appear very young, indicating that contraction may even continue today at very slow rates. The recognition that Mercury is still contracting was somewhat surprising to planetary scientists, who initially thought the process might have ended billions of years ago. The presence of young-looking scarps suggests that Mercury's interior is still cooling and still shrinking, though the rate of shrinkage has decreased significantly since early in the planet's history. The total amount of recent contraction is small, perhaps only a kilometer or so of radius decrease in the last billion years. But the fact that any contraction continues makes Mercury more geologically active than previously believed. Walking up to the base of a large scarp-like discovery roots, you would see a cliff face rising at an angle steeper than most slopes on Earth. The rock fractured and broken along the fault line. The cliff would cast deep shadows in the harsh sunlight, the shadowed areas completely black against the brightly lit surroundings. Boulders and debris fallen from the cliff face over billions of years would litter the ground at the base, each rock freed from the cliff by impacts, thermal stress, or the slow process of fault movement. The cliff would extend in both directions beyond your view, curving slightly as it follows the underlying geometry of the fault. Looking at the terrain on top of the scarp compared to below it, you would notice that the elevated section consists of the same types of features as the lower section, just raised by the fault motion. Craters that existed before the fault formed can sometimes be found split by the scarp, one half elevated relative to the other. These offset craters provide clear evidence of the vertical motion along the fault, with the amount of offset indicating how much displacement has occurred. The largest scarps show offsets of several kilometers, meaning the hanging wall block has been thrust up and over the footwall block by that distance. The sinuous paths that many scarps follow result from the three-dimensional geometry of the underlying thrust faults. Faults are not vertical walls, but rather inclined planes, typically dipping at angles of 20 to 40 degrees beneath the surface. As these inclined fault planes intersect the curved surface of Mercury, they create paths that curve and meander. The exact path depends on the dip angle of the fault, the topography it intersects, and the particular stress conditions that initiated faulting. The result is scaps that wind across the landscape rather than running in straight lines. Some regions show multiple scarps crossing each other at different angles, evidence of compression from different directions at different times. When two scarps intersect, the cross-cutting relationships reveal which formed first. The younger scarp will cut across the older one without being deflected. These relationships help scientists work out the sequence of events in Mercury's tectonic history, understanding how the stress patterns changed as the interior cooled and contracted. The picture that emerges is complex, with compression occurring over billions of years and not always in the same direction. The discovery that Mercury has globally distributed thrust faults came as somewhat of a surprise when Mariner 10 first revealed them clearly in the 1970s. Before spacecraft observations, Mercury was expected to be a simple cratered world, similar to the Moon. The presence of these tectonic features indicated that Mercury's interior had been more dynamic than anticipated, cooling and shrinking significantly over geological time. Later missions, particularly Messenger, revealed even more scarps and provided evidence for more recent activity, further refining our understanding of Mercury's evolution. The scarps create topographic barriers that segment the surface into distinct regions, each bounded by the cliffs and elevated or depressed relative to its neighbors. This topographic variation adds complexity to Mercury's landscape beyond what craters alone would create. The cliffs would be significant obstacles for any future exploration by rovers, requiring either careful route planning to go around them or specialized equipment to climb them. For a hypothetical human explorer on foot, the largest scarps would represent serious mountaineering challenges, multi-kilometer cliff faces in hostile environmental conditions. The formation of scarps affects more than just surface topography. The faulting may have created pathways for volcanic magma to reach the surface in some locations and time periods. The fracturing of the crust along thrust faults could provide avenues for rising magma, potentially explaining some of the volcanic features seen on Mercury. The relationship between tectonic activity and volcanism is complex, with each process potentially influencing the other. Some smooth plains appear to be associated with or bounded by scarps, suggesting possible connections between contraction and volcanic resurfacing. As impressive as these scarps are, Mercury's surface holds one more category of surprising features: regions hidden from the sun's heat, despite being on the planet closest to our star. These permanently shadowed areas exist near the poles and contain materials that seem paradoxical given Mercury's proximity to the sun. Near Mercury's north and south poles, the landscape takes on a character different from the sun-baked equatorial regions, though the rock and regolith remain fundamentally the same. Here, the sun never rises high in the sky because Mercury's axis of rotation is tilted only about 2 degrees from perpendicular to its orbital plane. This nearly upright orientation means that at high latitudes, the sun's path across the sky stays very close to the horizon, never climbing more than a few degrees above it. Where craters exist with walls tall enough to block this low-angle sunlight, their floors remain in permanent shadow, never receiving direct illumination. The floors of these permanently shadowed craters have not seen sunlight since they formed, possibly for billions of years if the crater is old enough. The shadows create cold traps, where temperatures never rise above about -200 degrees Celsius, far colder than the sunlit regions only kilometers away. This extreme cold persists because no sunlight reaches the shadowed areas to warm them, and no atmosphere exists to transport heat from elsewhere. The shadowed regions radiate their heat into space and into their surroundings until they reach an equilibrium temperature determined only by the faint thermal radiation from crater walls and the negligible heat from Mercury's interior. The existence of permanent shadows on the planet closest to the Sun seems almost contradictory, a quirk of geometry that creates perpetual darkness on a world otherwise dominated by intense sunlight. The conditions in these shadows are colder than anywhere in the outer solar system that receives occasional sunlight, colder even than some surfaces on Saturn's moons or Pluto's plains that periodically catch glimpses of the distant Sun. The coldest spots in the entire solar system that are not in eternal darkness exist on Mercury, hidden at the bottoms of polar craters. In these cold traps, water ice can survive indefinitely, despite the planet's proximity to the Sun and the baking heat just beyond the crater rims. The low temperature prevents the ice from sublimating into vapor, and the permanent shadow means no sunlight strikes the ice to provide energy for phase change. Water molecules that happen to migrate into these shadowed regions, delivered by comet and asteroid impacts over billions of years, freeze onto the cold surface and remain there. The ice accumulates slowly over geological time, building deposits that range from centimeters to meters thick, depending on location and age. Evidence for ice in Mercury's polar craters came first from radar observations made from Earth in the early 1990s. Radio telescopes bounced radar signals off Mercury, and the returned signals from the polar regions showed characteristics consistent with water ice: high reflectivity and a polarization pattern matching what ice produces. The radar-bright regions corresponded closely with the locations of permanently shadowed craters mapped by earlier spacecraft, strengthening the interpretation that the bright signal came from ice deposits. Later, the Messenger spacecraft confirmed the presence of ice through multiple independent measurements, establishing definitively that Mercury harbors significant water ice at its poles. The total amount of ice may exceed hundreds of billions of metric tons distributed across both polar regions, though estimates vary depending on assumptions about ice thickness and extent. The deposits cluster in craters poleward of roughly 80 degrees latitude, where permanent shadows are most common and most persistent. Some ice appears as relatively pure water ice deposits, while other areas show ice buried beneath a darker layer of organic material. The buried ice may be older, with later deposition of organic compounds creating an insulating blanket that protects the ice from what little heating does occur. The organic material covering some ice deposits probably arrived from the same source as the ice itself: carbon-rich comets and asteroids that impacted Mercury throughout its history. These impactors delivered both water and organic compounds, with both substances able to survive in the cold traps once they arrived. The organic layer helps insulate the ice below, reducing sublimation losses and potentially explaining why some deposits appear older and more extensive than others. The dark organics absorb any scattered light that does reach them, converting it to heat that nonetheless is not enough to vaporize the ice beneath due to the insulating properties of the covering layer. Standing at the rim of a permanently shadowed crater, you could look down into absolute darkness a blackness deeper than any night on Earth, because no light scatters into the shadow to provide even faint illumination. The stars overhead would provide the only light source, far too faint to reveal any details of the crater floor below. The boundary between sunlight and shadow would be razor sharp. Your position in brilliant light or total darkness determined by whether you stood a single step outside or inside the shadow line. The temperature would drop precipitously upon crossing into shadow, plunging hundreds of degrees within the distance of a footstep. If you descended into one of these shadowed craters, equipped with lighting, you would find a floor covered in frost and ice, bright white material contrasting with the dark regolith visible in other locations. The ice would be rock hard at these extreme cold temperatures, frozen more solidly than any ice on Earth ever becomes naturally. The surface might appear smooth if the ice is relatively pure, or rough and irregular if organic material is mixed in or layered on top. The unchanging cold would feel profound, a chill that represents the lowest temperatures experienced on any solid planetary surface, aside from occasional shadows on other airless bodies. The ice deposits provide a record of water delivery to the inner solar system over billions of years, each molecule representing a fragment of a comet or asteroid that wandered too close to the Sun and struck Mercury. The total amount of water locked in these polar ice deposits is tiny compared to Earth's oceans, but significant compared to water on other inner solar system bodies. More ice may be frozen in Mercury's polar regions than exists in some of Mars's ice deposits, a surprising comparison given Mercury's proximity to the Sun and Mars's position farther out. The discovery of water ice on Mercury has implications for future exploration and even for hypothetical resource utilization. Water is valuable for human space exploration, both as a source of drinking water and as a material that can be split into hydrogen and oxygen for rocket propellant. Having water resources at Mercury would make exploration more feasible, though accessing ice at the bottom of permanently shadowed craters presents obvious challenges. The extreme temperature difference between sunlit and shadowed areas complicates any engineering design, requiring systems that can handle both extreme heat and extreme cold. The polar regions also host areas of permanent or near-permanent sunlight, locations where the sun never sets or sets only briefly during certain parts of Mercury's orbit. These peaks of eternal light exist on the rims and central peaks of some polar craters, elevated enough to remain in sunlight, while the floors far below stay in permanent shadow. The combination of permanent sunlight and nearby permanent shadow creates one of the most extreme environmental contrasts anywhere in the solar system, with locations separated by a few kilometers experiencing temperature differences of 600 degrees or more. A future base on Mercury might be located at one of these polar sites, where sunlight is reliably available for solar power, while cold traps nearby offer access to water ice. The engineering challenges would be formidable, but the resources available, constant sunlight for energy, water ice for life support and propellant, and minerals in the regolith for construction, could make such a location viable. For now, these remain speculative possibilities, but they illustrate how Mercury's extreme conditions also create unique opportunities. The existence of permanently shadowed craters and the ice they contain demonstrates that even on the planet closest to the Sun, cold, dark places exist where water can survive unchanged for billions of years. The contrast between Mercury's sun-blasted equatorial regions and its frigid polar shadows shows that a planet's environment can vary dramatically depending on local conditions. The ice deposits await further study, each molecule potentially carrying information about the early solar system and the delivery of water to the inner planets. And understanding these polar regions requires understanding Mercury's unusual rotation, a pattern of day and night unlike anywhere else among the planets. The relationship between day and night on Mercury follows a pattern so unusual that it confuses initial understanding until the geometry becomes clear. Mercury rotates on its axis once every 58.6 Earth days, a leisurely pace compared to Earth's 24-hour rotation. At the same time, Mercury orbits the Sun once every 88 Earth days, completing its year in just under 3 times the length of its day. These two periods are locked in what is called a 3-to-2 resonance, with Mercury rotating exactly 3 times for every 2 orbits around the Sun. The resonance formed over billions of years as the Sun's gravity acted on Mercury's slightly non-spherical shape, the tidal bulge raised by solar gravity, creating torques that gradually slowed Mercury's rotation. The rotation slowed until it reached the current 3-to-2 relationship with the orbital period, at which point the configuration became stable. This is not quite a tidal lock like the Moon's 1-to-1 relationship with Earth, where the same face always points toward the larger body. Instead, Mercury rotates relative to the Sun in this 3-to-2 pattern, allowing all longitudes to eventually experience daylight and darkness. The combination of the rotation period and the orbital period produces a solar day, the time from noon to noon at any given location, of 176 Earth days. This means if you stood in one spot on Mercury's surface, you would experience approximately 88 Earth days of continuous sunlight, followed by 88 Earth days of darkness. The Sun would crawl across the sky over the course of weeks, its motion imperceptible from minute to minute, or even from hour to hour, but clearly progressing when observed over days. Watching the Sun's motion across Mercury's sky reveals behavior that occurs nowhere else among the planets, a consequence of Mercury's elliptical orbit, combined with its rotation rate. Mercury's orbit has the highest eccentricity of any planet except the dwarf planet Pluto, ranging from 46 million kilometers at perihelion to 70 million kilometers at aphelion. This elliptical path means Mercury's orbital speed varies significantly depending on where it is in its orbit, moving fastest at perihelion and slowest at aphelion, according to Kepler's laws of planetary motion. At perihelion, when Mercury races closest to the Sun, the planet's orbital angular velocity temporarily exceeds its rotational angular velocity from the perspective of someone standing on the surface. This creates the remarkable situation where the Sun's apparent motion across the sky stops, reverses direction briefly, then stops again and resumes its original direction. The Sun appears to move backward in the sky for several Earth days, a retrograde motion that seems to violate the expected east to west progression from certain specific longitudes on Mercury. This retrograde motion of the Sun creates an even stranger phenomenon, a double sunrise or double sunset. At these locations, you could watch the Sun rise slowly above the eastern horizon over several Earth days, climbing perhaps 10 or 20 degrees into the sky. Then, As Mercury passes through perihelion, the Sun would stop its climb, move backward toward the horizon, and set again in the east, where it had risen. After this temporary setting, the Sun would rise again from the same point and continue its journey across the sky toward the western horizon, where it would eventually set for the long night. The two longitudes where this double sunrise occurs are the hot poles, the points on Mercury's equator where the Sun is directly overhead at perihelion. These are the hottest locations on Mercury because the Sun not only comes closest, but also lingers in the sky due to the retrograde motion, delivering maximum solar heating over an extended period. The hot poles are separated by 180 degrees of longitude on opposite sides of the planet, positioned by Mercury's orbital geometry. The term hot pole is somewhat misleading, as these are equatorial locations rather than polar, but the name has stuck in the scientific literature. At longitudes 90 degrees away from the hot poles, observers would witness a different strange phenomenon. The Sun, at noon, appears to stop its motion across the sky, move backward toward the morning horizon, then stop again and resume its afternoon descent toward sunset. The midday sun would seem to pause in the sky, creating an extended period of maximum heating, even though this location does not reach quite the temperatures of the hot poles. This retrograde midday motion occurs because perihelion happens when these longitudes face the Sun at local noon. The long solar day means that temperature changes unfold very slowly as the Sun progresses across the sky, or as night continues in darkness. Sunrise on Mercury is not a brief event measured in minutes, but a gradual process taking Earth weeks as the Sun's disk slowly appears above the horizon. The leading edge appears first, a brilliant sliver of the solar disk becoming visible and gradually widening as more of the Sun rises into view. The sunlight creeps across the landscape, the boundary between shadow and light, advancing at roughly 10 kilometers per hour, slower than a leisurely bicycle ride on Earth. As the Sun climbs higher over the course of weeks, the shadows rotate around rocks and crater rims, shortening as the Sun approaches noon and lengthening again as afternoon progresses into evening. The temperature climbs steadily. With the Sun's elevation, the ground absorbing more and more solar energy and heating toward the maximum temperatures reached when the Sun is highest. The heating does not stop immediately when the Sun reaches its highest point, because the ground continues absorbing energy faster than it radiates it away. So maximum temperatures occur somewhat after local noon. Sunset reverses the process over another extended interval, the Sun slowly descending towards the western horizon, while temperatures gradually decline. The Sun's disk touches the horizon and begins to disappear below it, the process taking weeks as less and less of the solar disk remains visible. The shadows lengthen dramatically as the Sun approaches the horizon, rocks and crater rims casting shadows that extend for kilometers. Finally, the last bright sliver of the Sun drops below the horizon, and the long night begins, darkness descending immediately without the twilight that Earth's atmosphere creates. Night continues for 88 Earth days, the surface cooling continuously as it radiates heat into space, without any incoming solar radiation to replace what is lost. The temperature drops from the daytime high toward the nighttime low, a decline of over 600 degrees Celsius at equatorial latitudes. The cooling is faster at first when the surface is hottest, and slows as temperatures decline, but it continues throughout the long night. By the end of night, the ground has reached its minimum temperature, frozen far colder than any natural location on Earth. The stars wheel overhead during the long night, their apparent motion much faster than the sun's due to Mercury's orbital motion, adding to or subtracting from the rotational motion. The stars complete a circuit across the sky roughly every 7 Earth days at equatorial latitudes, the stellar day much shorter than the solar day. Any planets visible in Mercury's sky would also move against the stellar background. Venus and Earth sometimes appearing near each other as brilliant evening or morning stars as seen from Mercury's darkened surface. The approach of sunrise reverses the cooling trend, the ground beginning to receive solar heating again as the sun's leading edge appears above the horizon. The temperature begins climbing immediately as sunlight strikes the regolith, the dark surface, efficiently absorbing the radiation and converting it to heat. The transition from night to day thermally happens over weeks rather than minutes, giving the ground time to warm gradually from its frozen state. This slow heating means that thermal stress on surface materials is less severe than if the temperature change happened quickly. The combination of Mercury's orbital eccentricity and its 3:2 spin-orbit resonance creates variations in how much solar heating different longitudes receive. The hot poles experience the most extreme heating because they face the sun at perihelion when solar intensity is maximum, and the sun's retrograde motion causes it to linger. Locations 90 degrees away in longitude receive less total heating because they experience their noon at aphelion when the sun is farther away and less intense. The difference in total solar energy received over a complete day-night cycle creates permanent temperature variations tied to longitude. These temperature variations driven by longitude are unusual. Most planetary surfaces show latitude variations due to the tilt of the rotation axis, with polar regions cooler than equatorial regions. Mercury shows this latitude effect too, with its poles being generally cooler than the equator, but the longitude effect, superimposed on top, is unique to Mercury among the planets. The hot poles are hotter than other equatorial latitudes because of their geometric relationship to perihelion, not because of any intrinsic difference in the surface materials. Understanding this strange dance between rotation and orbit helps explain many of Mercury's surface features and environmental conditions. The long day-night cycle affects surface chemistry, with materials exposed to sunlight for months having different reactions occur than materials in shadow. The extreme temperature variations create stresses that fracture rocks and slowly break down surface materials through repeated thermal expansion and contraction. The retrograde motion of the sun concentrates heating in specific locations, potentially affecting where volcanic activity occurred or how crater materials weathered over time. And this unusual rotation pattern, combined with the absence of atmosphere, creates the temperature extremes that define Mercury's environment more than any other factor. The temperature swings experienced on Mercury's surface exceed those of any other solid surface in the solar system, a range from extreme heat to extreme cold that would seem impossible on a single world. At the subsolar point on the equator, during perihelion, when the sun is directly overhead at its closest approach, the surface temperature can reach approximately 430 degrees Celsius. This is hot enough to melt lead, which liquefies at 327 degrees, and zinc, which melts at 420 degrees. Tin would puddle on the ground at these temperatures, and even some forms of sulfur would begin to soften and deform. At night, after 88 Earth days without sunlight, the temperature at the same location plunges to approximately -180 degrees Celsius. This is colder than the coldest temperature ever recorded on Earth's surface, colder than winter in Antarctica, colder than the average temperature on Mars. The range between daytime maximum and nighttime minimum exceeds 600 degrees Celsius, a temperature swing that places enormous stress on any material experiencing it. Rock expands when heated and contracts when cooled, and the extreme temperature variations on Mercury cause continuous expansion and contraction that slowly fractures surface materials. The extreme temperatures result from three factors working in combination: Mercury's proximity to the Sun, the absence of atmosphere, and the very long day-night cycle. Proximity means Mercury receives roughly 7 times more solar energy per unit area than Earth when both planets are at their average distances from the Sun. At perihelion, when Mercury is closest, this factor increases to about 11 times Earth's solar input. This intense radiation would heat any exposed surface to high temperatures, even if day and night cycled quickly. The absence of atmosphere means no heat can be transported from the day side to the night side. No convection or conduction through air to moderate temperature extremes. On Earth, our atmosphere circulates heat globally, with winds carrying warmth from equator to poles and from day side to night side. This circulation keeps nighttime temperatures from dropping as low as they would otherwise, and it prevents daytime temperatures from rising as high. Mercury has no such moderation. Each location's temperature depends almost entirely on whether it receives sunlight at that moment and how much time has passed since the heating or cooling began. The long day-night cycle allows temperatures to climb higher during the day and drop lower during the night than would occur with faster rotation. 88 Earth days of continuous sunlight gives the surface ample time to absorb solar energy and heat to equilibrium temperature, where absorbed radiation balances radiated heat. A faster rotation would mean less time in sunlight, limiting how hot the surface could get. Similarly, 88 days of darkness provides time for the surface to radiate away nearly all its heat, cooling to temperatures determined only by the faint heat from the interior and thermal radiation from distant surroundings. The heating process during Mercury's day follows a predictable pattern determined by the changing altitude of the Sun and the time available for heat absorption. When the Sun first rises, the surface begins warming from its minimum nighttime temperature. The early morning sun is low in the sky, so its rays strike the surface at a shallow angle, spreading the energy over a larger area and providing less heating per unit surface area. As the sun climbs higher over the course of weeks, the rays strike more directly and the heating intensifies. Maximum temperature occurs somewhat after local noon because the surface takes time to reach equilibrium with the incoming radiation. Even when the sun passes its highest point and begins descending, the ground continues receiving more energy than it radiates away, so the temperature keeps climbing for some time. Eventually, outgoing radiation balances incoming radiation, and the temperature peaks. After this point, the declining angle of the afternoon sun means less incoming energy, and the temperature begins to drop, even though the sun remains well above the horizon. The cooling during sunset and night follows a curve determined by radiation physics, with the rate of cooling dependent on the current temperature. Hot surfaces radiate energy according to the Stefan-Boltzmann law, which states that radiated energy increases with the fourth power of absolute temperature. This means very hot surfaces cool faster than warm surfaces. When night first begins and the surface is still hot from the long day, the cooling is relatively rapid as the surface radiates intense infrared energy into space. As the surface cools, the radiation rate decreases and the cooling slows. By the end of the long night, the temperature has dropped to values where the surface radiates very little energy, and the cooling has become very slow. The final nighttime temperature represents a balance between the negligible heat arriving from the interior and distant surroundings versus the radiation being emitted by the cold surface. If night lasted much longer than 88 Earth days, the temperature would drop only slightly lower because the surface is already approaching its equilibrium value. The regolith covering Mercury's surface acts as an effective insulator despite being exposed directly to the temperature extremes. The loose, powdery material contains countless tiny spaces between grains where near-perfect vacuum exists. These vacuum gaps prevent conductive heat transfer between grains, so heat can only move through the regolith slowly by radiation from one grain to the next. The result is that temperature changes penetrate only a limited distance below the surface, perhaps a meter or two, while deeper material remains at much more stable temperatures. This insulating effect means that during the day, the top few centimeters of regolith become extremely hot, while material just a meter below remains much cooler. Similarly, at night, the surface layer freezes, while slightly deeper material retains some warmth from the previous day. If you could dig down into Mercury's regolith and measure temperature with depth, you would find that the wild swings at the surface moderate rapidly with depth, becoming nearly constant a meter or two down. This stable temperature at depth is much more moderate than either the daytime high or nighttime low at the surface. The bedrock beneath the regolith experiences even less temperature variation, its higher thermal conductivity and larger mass helping to average out the extremes. Deep inside Mercury, perhaps tens of meters below the surface, the temperature probably varies hardly at all over the course of a day-night cycle, determined instead by the slow flow of heat from the planet's interior toward space. This creates a permanent temperature gradient, warmer at depth and colder near the surface, with the surface layer oscillating above and below the deep, stable temperature. The temperature extremes affect surface chemistry in ways that would not occur on more moderate worlds. At high temperatures, certain chemical reactions proceed that cannot happen in the cold, while at low temperatures, different reactions become possible. The repeated cycling between hot and cold may drive chemistry in directions different from what would occur at constant intermediate temperatures. Some minerals are stable at high temperatures, but transform to different structures when cooled, and the repeated transformation may create unique mineral assemblages on Mercury's surface. The expansion and contraction of rock, due to temperature cycling, causes physical weathering separate from the chemical weathering occurring at the same time. Rocks expand when heated and contract when cooled, and different minerals within a rock may expand at different rates. This differential expansion creates internal stresses that slowly crack the rock, eventually breaking it into smaller pieces. Over millions of years, this thermal stress weathering contributes to the production of regolith, grinding down bedrock into smaller and smaller fragments. The extreme temperatures also affect how we would need to engineer any spacecraft or equipment intended to operate on Mercury's surface. Materials must withstand both extreme heat and extreme cold without losing structural integrity or functionality. Electronics typically have limited temperature ranges where they function properly, requiring careful thermal management with heaters for cold periods and radiators or reflective insulation for hot periods. Solar panels would be incredibly efficient during the day due to high solar intensity, but would need to survive both the heat and the subsequent cold night. Any future human exploration of Mercury would need to account for these temperature extremes in habitat design, spacesuit engineering, and operational planning. Working during the day would require excellent thermal protection against heat, while working at night would require protection against cold. The slow transition between day and night might offer operational windows during morning and evening when temperatures are more moderate, though even these periods would be extreme by Earth standards. The poles, with their mixture of permanent sunlight and permanent shadow, might offer more stable thermal environments. The temperature extremes on Mercury illustrate what happens when several factors align to create the most extreme conditions possible on a planetary surface. Proximity to a star, lack of atmosphere, and slow rotation combine to produce a thermal environment unique in the solar system. Understanding these extremes helps scientists understand planetary heat budgets and surface-atmosphere interactions more generally. And these extremes result from Mercury's unusual structure, particularly the enormous iron core that dominates the planet's interior mass. Deep beneath the surface of Mercury lies a structure that makes this planet fundamentally different from any other terrestrial world in the solar system. The iron core that occupies Mercury's interior is disproportionately large compared to the planet's total size, comprising roughly 85% of the planet's radius. To put this in perspective, if you could cut Mercury in half and look at the cross-section, you would see a huge ball of iron surrounded by a relatively thin shell of rock. This structure is radically different from Earth, where the core makes up only about 55% of the radius, or Mars, where the core is roughly 50%. The core's dominance means that by volume, roughly 75% of Mercury's interior is metallic iron and nickel, with the remaining 25% being rocky mantle and crust. By mass, the proportion is even more extreme. Approximately 70% of Mercury's total mass is the iron core. This makes Mercury the most metal-rich planet in the solar system, relative to its size. A characteristic that has puzzled scientists since the high density was first measured from observations of Mercury's gravitational effect on spacecraft trajectories. Mercury's overall density is 5.43 grams per cubic centimeter, second only to Earth at 5.51 grams per cubic centimeter among the terrestrial planets. However, this comparison is somewhat misleading because density is affected by gravitational compression, the weight of outer layers compressing inner layers to higher density. If you could somehow remove the compression caused by self-gravity, Earth's uncompressed density would be about 4.4 grams per cubic centimeter, while Mercury's would be about 5.3 grams per cubic centimeter. This uncompressed density reveals that Mercury's material is intrinsically denser than Earth's, reflecting the higher proportion of iron. The core consists of two distinct regions, an outer liquid layer and an inner solid sphere. We know the outer core is liquid because Mercury possesses a global magnetic field, and the most likely mechanism for generating such a field is a dynamo process in a liquid electrically conductive layer. As the liquid iron flows and churns in the outer core, driven by convection from heat loss, the motion creates electrical currents. These currents generate magnetic fields, which in turn affect the fluid motion, creating a self-sustaining dynamo that maintains Mercury's magnetic field. The magnetic field itself is weak compared to Earth's. Only about 1% the strength at Mercury's surface compared to Earth's surface field. Nonetheless, the mere existence of any internally generated magnetic field tells us important information about the core's state. The field indicates that despite Mercury's small size and presumed rapid cooling, the outer core remains liquid today, more than 4 billion years after the planet formed. The inner core, by contrast, has solidified as cooling proceeded, and the freezing temperature isotherm migrated outward, growing the solid inner core at the expense of the liquid outer core. The mantle surrounding the core is remarkably thin, only about 400 kilometers thick from the top of the core to the base of the crust. This is a thin shell indeed compared to Earth's mantle, which extends about 2,900 kilometers from core to crust. Mercury's thin mantle means the metallic interior comes much closer to the surface proportionally than on any other terrestrial planet. The mantle consists primarily of silicate minerals similar to Earth's mantle. Compounds of silicon, oxygen, magnesium, and iron in various combinations, though possibly with a different mix of minerals due to Mercury's unusual formation conditions. The crust is even thinner than the mantle, averaging only about 35 kilometers thick, based on gravity data and impact basin observations. Some areas may have thicker crust, while others are thinner, but the average is remarkably thin compared to Earth's continental crust, which averages about 35 to 40 kilometers, but reaches 70 kilometers under mountain ranges. The thinness of Mercury's crust, combined with the thin mantle, means the total thickness of rocky material overlying the iron core is only about 435 kilometers, roughly 1/6 of Mercury's total radius. The question of why Mercury has such a large iron core relative to its rocky envelope has no single agreed-upon answer, though several hypotheses have been proposed and tested against observations. One early idea suggested that a giant impact early in Mercury's history stripped away much of the rocky mantle, leaving behind the iron core, surrounded by only a thin remaining shell. According to this scenario, Mercury originally had a more Earth-like proportion of rock to metal, but a collision with another large object blasted away perhaps 60% of the rocky material, which either escaped Mercury entirely or reaccreted in a thinner layer. An alternative hypothesis proposes that intense heat from the early sun vaporized much of the silicate rock from the proto-Mercury before it finished accreting, leaving behind a more iron-rich body. In this model, Mercury formed from the solar nebula in the hottest region of the disk, where the forming sun's heat was most intense. Light elements and compounds like silicates would have been more easily vaporized than the heavier iron particles, leading to a depletion of the former and an enrichment of the latter in the material that eventually formed Mercury. A third possibility involves chemical fractionation in the solar nebula itself, where different materials condensed at different temperatures as the nebula cooled. In the hot inner regions where Mercury formed, perhaps only the most refractory materials, those with the highest condensation temperatures, could remain as solids. Iron condenses at higher temperatures than many silicate minerals, so the material available for building Mercury may have been naturally enriched in iron compared to material farther from the Sun. This would explain Mercury's composition as a natural consequence of where it formed, rather than requiring a specific event like an impact or extreme heating episode. Each hypothesis makes slightly different predictions about surface composition and internal structure, and ongoing analysis of messenger data continues to test these ideas. The discovery that Mercury's surface is relatively low in iron compared to expectations has complicated the picture. If a giant impact stripped away the mantle, we might expect the remaining mantle material to show evidence of that event in its composition. Similarly, the discovery of relatively high amounts of volatile elements like sulfur and potassium on the surface challenges the idea that extreme heating vaporized away all light elements, regardless of how Mercury obtained its unusual structure. The large iron core has important consequences for the planet's evolution and current state. The core contained enough heat from formation and from radioactive decay to remain partially molten even today, allowing the magnetic field to persist. As the core cools and the inner core grows through solidification, latent heat is released that helps power convection in the outer core. This process may allow Mercury's magnetic field to persist for billions of years into the future, though it will likely weaken as the core continues to cool. The large core also affects how much Mercury has shrunk over its lifetime. As iron solidifies from liquid to solid during inner core growth, it becomes slightly denser, occupying less volume. The core's contraction pulls the overlying mantle and crust inward, requiring them to contract as well to accommodate the reduced circumference. The dramatic shrinking of Mercury's radius by about 7 kilometers since formation results partly from core cooling and partly from simple thermal contraction as the entire planet cooled from its hot initial state. The large proportion of iron in the core magnifies this effect compared to planets with smaller cores. The composition of the core is primarily iron, with perhaps 15 to 20% nickel, similar to iron meteorites and to Earth's core. Some lighter elements are probably present in small amounts, perhaps sulfur and silicon, which would lower the core's melting temperature and affect its density. The exact mixture of light elements dissolved in the core remains uncertain, an important detail that would affect predictions of core behavior and evolution. Future missions to Mercury may be able to constrain this composition through more precise gravity measurements, and seismometers are ever placed on the surface. The presence of a magnetic field allows Mercury to partially deflect the solar wind, creating a small magnetosphere around the planet. This magnetosphere is much weaker and smaller than Earth's, extending only about 1 to 2 Mercury radii from the planet's center, rather than Earth's 10 radii or more. The weak field means that Mercury's surface is still exposed to significant solar wind bombardment, but the magnetosphere provides some protection and creates interesting interactions between the solar wind and Mercury's exosphere. The internal heat remaining in Mercury is now quite low, with most of the initial heat of formation and radioactive heating having been radiated away over billions of years. The heat flow from the interior to the surface is probably only about 1/10 of Earth's or less, meaning Mercury's interior is approaching a cold state where geological activity will eventually cease entirely. The survival of liquid outer core today represents the last vestiges of Mercury's initial heat budget, slowly draining away as the planet cools toward equilibrium with its environment. Understanding Mercury's interior structure helps scientists understand planetary formation and differentiation processes. More generally, Mercury represents an end-member case, a planet with the most extreme iron enrichment we know of, and understanding how this came to be illuminates the range of outcomes possible in terrestrial planet formation. The large core also makes Mercury an important laboratory for studying core dynamos and magnetic field generation under different conditions than Earth provides. Every detail we learn about Mercury's interior adds to our understanding of how rocky planets work and how they evolve. And tracing that evolution backward leads to questions about Mercury's formation and early history in the violent youth of the solar system. Mercury formed approximately 4.5 billion years ago from the disk of gas, dust, and larger fragments orbiting the newborn sun, the same disk that gave birth to all the planets. The inner regions of this protoplanetary disk, where Mercury would eventually form, were hot due to proximity to the forming sun and due to the energy released by countless collisions of accreting material. Temperatures likely exceeded 1,000 degrees Celsius, high enough that only refractory materials, metals like iron and minerals like olivine that can withstand extreme heat, remained as solids. Lighter elements and volatile compounds were driven outward by radiation pressure and by the heat itself, creating a composition gradient across the disk. Small grains of iron and rocky minerals in this hot inner region stuck together when they collided, the beginning of planet building. Electrostatic forces helped tiny particles adhere, while collisions at just the right velocity allowed larger fragments to merge rather than bouncing apart. The process was gradual at first, building from dust grains to pebbles to boulders to kilometer-sized objects called planetesimals. Over perhaps 100,000 years, these planetesimals represented the first substantial solid bodies in the forming solar system, each one growing by sweeping up material from its orbital path. As planetesimals reached sizes of 10 kilometers or larger, their gravity became significant enough to start pulling in nearby material more effectively. The largest planetesimals grew fastest, their greater mass giving them stronger gravitational pull to attract more material. Eventually, a few dominant bodies emerged in the inner solar system, protoplanets that would become Mercury, Venus, Earth, and Mars. These protoplanets continued to grow through violent collisions with other large bodies, each impact adding mass and releasing tremendous energy as kinetic energy converted to heat. Mercury's growth proceeded through countless impacts over several million years, with the planet growing larger and hotter as material accreted. The energy released by impacts kept the growing planet molten throughout this period, the surface repeatedly vaporized by new collisions before it could solidify. The molten state allowed differentiation to proceed, with denser iron sinking toward the center and lighter silicates rising toward the surface. This gravitational separation created the core mantle crust structure we observe today. Though the exact proportions may have been modified later, by the processes discussed earlier. Giant impact, vaporization of silicates, or other mechanisms. The differentiation process released additional heat through gravitational potential energy being converted to thermal energy as dense material sank and light material rose. This heat added to the impact heating and to the heat from radioactive decay of elements like aluminum-26, which was present in the early solar system and decayed with a half-life of only 700,000 years. The combination of these heat sources kept Mercury molten for millions of years, allowing complete differentiation and likely leading to a magma ocean covering the entire planet. Eventually, the rate of large impacts declined as the inner solar system cleared out most of its debris, and Mercury's surface could solidify into a permanent crust. This first crust probably formed roughly 4.4 billion years ago, though it may have been repeatedly destroyed and reformed by later large impacts during the tail end of planet assembly. The crust that formed was composed of silicate minerals that crystallized from the cooling magma ocean, creating a solid shell around the still molten interior. This early crust may have been compositionally different from the current crust, as subsequent processes could have modified it. After the main phase of planet assembly ended, Mercury had reached approximately its current mass and radius, though its interior remained much hotter than today. The period from about 4.1 to 3.8 billion years ago is called the Late Heavy Bombardment, a time when the inner solar system experienced increased impact rates, possibly due to gravitational disturbances from the giant planets rearranging the orbits of asteroids and comets. During this period, Mercury and the other terrestrial planets were struck by many large objects, creating the oldest craters and basins we observe today. The Caloris Basin formed during this bombardment period, about 3.9 billion years ago, one of the last major impacts to strike Mercury. The impact was severe enough to have affected the entire planet, creating seismic waves that fractured the antipodal surface and possibly triggering volcanic activity by fracturing the crust and creating pathways for magma to reach the surface. Other large basins formed around the same time, reshaping Mercury's surface and excavating material from deep in the crust and upper mantle, mixing compositions in complex ways. Volcanic activity was significant on Mercury during and after the late heavy bombardment, with lava flows resurfacing large areas of the planet. These smooth plains appear lighter colored than the heavily cratered highlands and show fewer impact scars, indicating they formed after the heavy bombardment had largely ended. The volcanism may have been triggered by impacts fracturing the crust, or it may have been driven by heat from the interior, creating buoyant magma that rose through the mantle to erupt at the surface. The volcanic period lasted for perhaps several 100 million years before declining as the interior cooled and magma production decreased. The last major phase of volcanic activity probably ended around 3 to 3.5 billion years ago, leaving Mercury with essentially its current surface appearance. After this point, only occasional impacts have modified the surface, creating new craters but not fundamentally changing the landscape. The planet entered a long, quiet period dominated by slow cooling, ongoing contraction, creating the lobate scarps, and accumulation of impact craters at the declining rate characteristic of the modern solar system. The contraction of Mercury has continued throughout its history as the interior cools and shrinks. The total radius decrease of about 7 kilometers has occurred over 4 billion years or more, with the rate of shrinkage probably higher in the early phases when cooling was faster. The scarps we observe formed at various times over this long period, with the oldest scarps being degraded by subsequent impacts and the youngest appearing fresh. The discovery of apparently young scarps suggests that contraction may continue at very slow rates even today, making Mercury one of the few terrestrial planets showing evidence of recent tectonic activity. The surface composition has been modified over time by space weathering, impact gardening, and possibly by interactions with Mercury's weak magnetic field and the solar wind. The dark color of Mercury's surface reflects billions of years of micrometeorite bombardment and solar wind sputtering that has altered the chemistry of the topmost layers. The higher concentration of certain volatile elements, like sulfur, compared to predictions, may indicate late delivery by comets, or may reflect unusual chemistry in the crust that protected these elements from being lost. Mercury's magnetic field has likely existed since early in the planet's history, as long as the outer core has remained liquid, though its strength has probably decreased over time as the core cooled. The field has helped shield Mercury from the worst of the solar wind bombardment throughout the planet's history, though the protection is far less complete than Earth's stronger field provides. The interaction between the magnetic field and solar wind has created a miniature magnetosphere that has evolved as the field weakened and as solar wind conditions changed with the sun's own evolution. Looking at Mercury today, we see a planet that formed quickly, differentiated early, experienced heavy bombardment and volcanism, then settled into a long, slow cooling phase that continues in the present. The surface we observe preserves a record stretching back 3 to 4 billion years, ancient terrain that has changed little since forming. Mercury represents a world that completed its major evolution early in solar system history and has since been slowly winding down. Its geological activity nearly ceased, but not quite finished. Understanding this ancient world required sending human-built machines across the vast distance to observe what no human eye had ever clearly seen. For most of human history, Mercury remained a mysterious, bright point of light, visible only near sunrise or sunset, never straying far from the sun in our sky. Ancient astronomers tracked its wandering path across the stars, noting its regular appearances and disappearances as it orbited closer to the sun than Earth. The planet's proximity to the sun's glare made detailed telescopic observation difficult, revealing only a small disk showing phases like Venus, but little surface detail. Mercury kept its secrets well, hiding its true nature behind distance and the sun's overwhelming light, waiting for technology capable of crossing the void to examine it closely. The first human-built object to visit Mercury was Mariner 10, a spacecraft launched by NASA on the 3rd of November 1973, with a mission to explore both Venus and Mercury. Mariner 10 used a gravity assist from Venus to redirect its path toward Mercury, an early demonstration of the trajectory techniques that would become standard for outer solar system exploration. The spacecraft reached Mercury on the 29th of March, 1974, flying past at a distance of about 700 kilometers above the surface. The images returned during this first encounter revealed a heavily cratered world resembling the Moon, confirming that Mercury had preserved an ancient surface, largely unmodified by geological activity. Mariner 10 returned to Mercury for a second flyby on the 21st of September 1974. This time, passing the night side and capturing different regions than the first encounter had revealed. The spacecraft's orbit around the Sun had been carefully designed to bring it back to Mercury at regular intervals, using the planet's own orbital period to create resonance between the two paths. A third and final encounter occurred on the 16th of March, 1975, bringing the total mapped surface area to about 45% of Mercury's total. These three flybys provided humanity's first close look at the innermost planet, though more than half the surface remained unseen. The images from Mariner 10 showed extensive cratering, smooth plains likely volcanic in origin, and long cliff faces that suggested global contraction. Scientists identified the Caloris Basin during these flybys, though only half of it was in sunlight and visible to the spacecraft's cameras. The discovery of a weak magnetic field surprised the mission team, who had expected Mercury to have cooled enough to solidify completely, eliminating any possibility of a dynamo-generated field. This finding suggested that Mercury's core remained at least partially molten, an insight that would drive future investigations into the planet's interior structure. For over 3 decades after Mariner 10, no spacecraft visited Mercury, and the planet remained incompletely explored. Ground-based radar observations during this period detected something unexpected in the permanently shadowed polar craters. Bright reflections consistent with water ice, despite Mercury's proximity to the Sun. These tantalizing radar signals raised questions that could only be answered by returning to Mercury with more capable instruments. Planning began for a mission that would not simply fly past, but would enter orbit and study Mercury comprehensively over an extended period. The Messenger spacecraft, whose name stands for Mercury Surface, Space Environment, Geochemistry, and Ranging, launched on the 3rd of August 2004, beginning a journey that would take nearly 7 years. The trajectory required 1 Earth flyby, 2 Venus flybys, and 3 Mercury flybys before finally slowing enough to enter orbit around the innermost planet. Each flyby adjusted MESEGR's velocity and trajectory, gradually matching the spacecraft's path to Mercury's orbit, while managing the intense solar heating encountered this close to the Sun. The complex journey demonstrated the difficulty of reaching Mercury. Ironically, getting there requires more energy than reaching Jupiter in some respects. Messenger entered orbit around Mercury on the 18th of March, 2011, becoming the first spacecraft ever to orbit the planet and beginning a mission that would last over 4 Earth years. From orbit, MESEGR mapped the entire surface at high resolution, including the hemisphere Mariner 10 had never seen in sunlight. The spacecraft carried instruments to measure surface composition, magnetic field strength and structure, topography, and the tenuous exosphere that surrounds the planet. Over thousands of orbits, flying as low as 200 kilometers above the surface, Messenger collected data that revolutionized our understanding of Mercury's geology, chemistry, and history. The mission confirmed that water ice exists in permanently shadowed polar craters, mixed in some places with dark organic material that probably arrived on the same comets that delivered the ice. Messenger measured the planet's gravity field with high precision, revealing details about the interior structure and confirming that the outer core remains liquid. The magnetic field was mapped globally, showing it is offset from the planet's center. and weaker than previously thought. Volcanic vents, evidence of past explosive volcanism, and the surprising abundance of volatile elements all emerged from MESSENGER's patient observation of this harsh environment. You are listening to The Drowsy Astronaut, and as we continue our journey across Mercury's ancient surface, we turn now to the missions that allowed us to see this world clearly. The spacecraft that traveled millions of kilometers carried instruments built by human hands, operated by people working through the technical challenges of exploring a planet where temperatures swing across hundreds of degrees. Their efforts transformed Mercury from a bright point near the Sun into a known world, a landscape we can walk through in imagination, understanding what lies beneath our hypothetical boots. MESSENGER's mission was extended twice beyond its original one-year primary mission, allowing the spacecraft to continue gathering data until it finally ran out of propellant for maintaining its orbit. On the 30th of April 2015, MESSENGER completed its final planned observation, then descended and impacted Mercury's surface at about 3.9 kilometers per second, creating a crater estimated at 16 meters across. The impact site lies on the far side of Mercury as seen from Earth, in the planet's northern hemisphere, adding one more crater to a surface already marked by billions of years of impacts. Even as MESSENGER was completing its mission, another spacecraft was being prepared for launch. BepiColombo, a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency. BepiColombo launched on the 20th of October 2018, carrying two separate orbiters that will study Mercury from different perspectives. The Mercury Planetary Orbiter, built by ESA, will map the surface and interior structure, while the Mercury Magnetospheric Orbiter, built by JAXA, will study the magnetic field and its interaction with the solar wind. The two orbiters are traveling together during the long journey to Mercury, connected as a single stack until they arrive. The journey to Mercury takes BepiColombo over 7 years, following a trajectory even more complex than MESSENGER's path. The spacecraft will perform 1 Earth flyby, 2 Venus flybys, and 6 Mercury flybys before finally entering orbit in December 2025. Each flyby provides an opportunity to test instruments and collect data, gradually building anticipation for the comprehensive study that will begin once the orbiters separate and settle into their different orbital configurations. The long journey reflects the challenge of slowing down enough to be captured by Mercury's relatively weak gravity without plunging into the Sun. Once in orbit, BepiColombo's 2 spacecraft will complement each other's observations. The planetary orbiter studying the surface and interior, while the magnetospheric orbiter examines the space environment around Mercury. The combined mission aims to answer questions MESSENGER raised, including the exact composition of the surface, the structure of the magnetic field source in the core, the history of volcanic activity, and the processes that maintain Mercury's tenuous exosphere. The mission is designed to last 1 Earth year initially, with possible extensions if the spacecraft remain healthy in Mercury's challenging environment. Beyond BepiColombo, concepts for future Mercury exploration include landers that would touch down on the surface and analyze rocks directly. A lander would face extreme engineering challenges, surviving launch, the journey, landing, and then operating in an environment where temperatures can reach 430 degrees Celsius in sunlight. Thermal management would require sophisticated insulation and cooling systems, possibly placing the lander in a permanently shadowed region or operating only during Mercury's long night. Such a mission would provide ground truth for orbital observations and could analyze the mysterious hollows and the ice deposits in detail. Sample return from Mercury remains a distant dream, requiring technology to not only land, but also launch from the surface and return samples to Earth. The energy requirements are substantial because escaping Mercury's gravity well, while already deep in the Sun's gravitational influence, demands significant velocity changes. But the scientific rewards would be enormous. Laboratory analysis of Mercury rocks would reveal details about formation, differentiation, and evolution impossible to determine remotely. Future generations may develop the technology and resources to undertake such an ambitious mission, bringing pieces of the innermost planet back for direct study. The exploration of Mercury teaches us about the solar system's formation and evolution, revealing how planets form in the hot inner regions close to a star. The lessons learned at Mercury apply to understanding rocky planets around other stars, worlds we will never visit but can comprehend through analogy. Each discovery at Mercury adds to our understanding of planetary processes: differentiation, volcanism, magnetic field generation, space weathering, impact dynamics. The knowledge accumulates slowly, mission by mission, flyby by flyby, building a comprehensive picture of a world that once was only a bright point of light. Standing on Mercury's surface, in imagination, we feel the extremes that characterize this world. The enormous sun beating down with 7 times Earth's intensity. The ground baked to temperatures that would melt lead. The black sky overhead shows stars even at noon, the vacuum creating absolute silence, broken only by the crunch of regolith under boots. Looking around, the cratered landscape extends to a horizon closer than Earth's. The curvature of this small world more pronounced. The scene has remained essentially unchanged for billions of years and will persist for billions more. A frozen record of the solar system's violent youth. The Terminator creeps across the landscape at walking pace, taking Earth months to complete the transition from day to night or night to day. Standing in shadow, the temperature plunges toward nearly -200 degrees Celsius, cold enough to freeze carbon dioxide if any were present. The contrast between sunlight and shadow is absolute. No atmospheric scattering to soften the boundary, no twilight zone of gradual change. You could stand with one foot in blazing heat and the other in freezing shadow, experiencing both extremes simultaneously. Mercury continues its orbit around the Sun, completing its 88-day trip again and again. Its rotation locked in the 3-2 resonance that creates the strange solar motion visible from certain longitudes. The planet shrinks imperceptibly as its core continues cooling, new stress building in the crust that will eventually relieve itself through tiny shifts along thrust faults, creating new scarps or extending old ones. Impact craters accumulate slowly, the modern impact rate so low that centuries might pass between craters large enough to notice. Time moves slowly on a geological scale, but Mercury changes nonetheless, evolving even in its ancient maturity. The ice in the permanently shadowed craters waits in its cold traps accumulating molecule by molecule whenever a comet delivers water to the surface. The deposits grow thicker by tiny amounts each time, building layers that record Mercury's bombardment history in frozen form. This ice represents perhaps the most accessible water in the inner solar system beyond Earth, a resource that future human missions might utilize if we ever establish presence this close to the Sun. For now, the ice simply exists, undisturbed and patient, preserving information about the volatile delivery history of the inner planets. Mercury's story is one of extremes. The closest planet to the Sun, the smallest terrestrial planet, the planet with the largest core relative to its size, the greatest day-night temperature range, the most elliptical orbit among the planets. These superlatives make Mercury unique, a world defined by being first and smallest and most extreme. Yet, it is also simply another terrestrial planet, formed by the same processes that built Venus, Earth, and Mars, governed by the same physical laws that apply throughout the universe. Understanding Mercury helps us understand not just one planet, but the principles that govern all rocky worlds. The Sun that dominates Mercury's sky will eventually evolve into a red giant, swelling to perhaps 100 times its current radius in about 5 billion years. When that happens, Mercury will be engulfed by the Sun's outer atmosphere, spiraling inward through the tenuous gas and possibly vaporizing entirely. The planet that formed in the hot inner disk will finally return to the star, its atoms scattered or incorporated into the white dwarf remnant the Sun will become. But that ending lies billions of years in the future, time enough for countless civilizations to rise and fall, time enough for the universe to change in ways we cannot predict. For now, Mercury orbits on, the Sun's heat washing across its surface. During the long days, the deep cold of space claiming the surface during the long nights. The spacecraft we have sent observe and record, transmitting data across millions of kilometers to Earth, where scientists work to understand what the measurements mean. Our exploration continues because Mercury rewards curiosity with discovery, each observation revealing something new about this ancient, extreme, and fascinating world. The planet that seemed so simple from Earth, just a bright point near the Sun, has proven rich in complexity, deserving of the attention we have given it and the missions we plan to send. Tonight, Mercury continues its path around the Sun, indifferent to observation but open to understanding, a world of rock and iron and ancient impacts waiting in the inner solar system. The ground we have walked in imagination remains untouched by human presence, marked only by the impacts of asteroids and the slow work of temperature cycling, breaking rock grain by grain. Our machines have visited, orbited, and impacted, but the planet continues essentially as it has for billions of years. Extreme and quiet and patient. The nearest planet to the Sun, where day lasts months and shadows are black as space,